Mike Gibson and Dean Kereiakes coming to you virtually from TCT 2020. Dean, I'm really excited to hear what you have to say about this new technology, Disrupt CAD. Some of us, like myself, are not big fans of atherectomy due to distal embolization. So I'm very excited to see this kind of new type of technology. Talk to us a little bit about what you found.
Well, thanks a lot for the opportunity, Mike. Intravascular lithotripsy really applies the technology that's been used for over 30 years to treat kidney stones, and it packages it in a balloon. One of the novel things here, and I'll mention one of the endpoints or observations that I thought was so fascinating in the trial, is that they take a novel technology, leading edge technology, and they package it in the most primitive device that you and I use, dating to the days of Andreas Grunzing. It's a balloon.
Mm-hmm.
So the learning curve, distinctly different from the atheroablative technologies, is virtually non-existent.
Right. Yeah, I've used it a couple of times, and it was very easy to use. I agree.
It's simple. And so without telling you, I'll sneak that in right now. We had one roll-in per site, 47 international sites. And then we had 384 patients in an ITT population, which the primary endpoint at 30 days was derived. And the populations, 47 and 384, were clinically and angiographically similar.
Mm-hmm.
The outcomes in the first 47 patients were not different from the outcomes in the 384. So device crossing success, freedom from MACE at 30 days, procedure success. I mean, it really is pretty remarkable when you think about that's the learning curve, one case or less. So we did a single-arm, non-randomized trial of this technology, which is the lithotripsy in a balloon catheter, so to speak, the intent of which is to modify calcium, because this trial also, I think, definitively tells you what the mechanism is for the technology, because we had a 100-patient OCT substudy, very carefully studied. So it's a calcium modifying technique, single, non-randomized, and it was based on performance goals that we established from the predicate Orbit 2 trial, which was single-arm, non-randomized, IDE trial for orbital atherectomy. We use the same endpoints. We use the same definitions. CKMB greater than 3x, for example, we core labbed out because many hospitals don't even do CKMB anymore.
Yeah.
But that was the definition, the two. So at that time, so that's what we did. And we tried to enroll the same patient population. So the entrance criteria were radiopacity on both sides of the artery without contrast, at least 15 millimeters. Think about that, angiographically. Imaging, you had to have a calcium mark at least 270 degrees, at least. So you could get in either with, you weren't obligated to do imaging, but either way. So we enrolled those patients. It was powered based on the performance goals established. For primary safety performance goal was freedom from MACE at 30 days. Primary effectiveness performance goal, success. And that was defined as successful stent delivery with a less than 50% residual stenosis and no in-hospital MACE. Obviously, one criticism would be that's pretty archaic, it's antiquated, nobody uses less than 50 anymore for stent. So, but that's the primary endpoint that was used in Orbit 2. So we did sensitivity analysis using less than equal to 30%.
Sure.
Which is, and frankly, all the stent trials that we do now all have that. The FDA's embraced that. That's less than equal to 30% residual. So in that, the device hit a home run. We far exceeded the safety performance goal. The lower bound far exceeded the performance goal. The lower bound in the effectiveness far exceeded the performance goal. The total MACE to in hospital was 7%, and to 30 days, 7.8, which is less than the 10.4 that was noted in Orbit 2. In our population, when I tell you the Orbit 2 had a lesion length of 18.9, ours is 26. Orbit 2 had a calcified segment length of 28 millimeters. Ours is 48 millimeters calcified segment length. So when you look at that, really a rougher group of patients documented. The ARC of calcium average in the OCT was 293.
Wow.
And the average thickness, 0.96 millimeters, almost a millimeter. You mean CVI index score, is got less than 0.5 thickness, greater than 0.5 thickness to get a point. You get greater than 5 millimeters length to get a point, and an arc greater than 180 to get 2 points. This is off the chart. Mm-hmm. And despite that, the procedure success was 92. That means no MACE, 92.4, 92.2, I'm sorry, and we used the less than 30% for procedure success. It's 92.4.
Yeah.
There's no difference. And that was very important observation.
And that was, Dean, 30% by QCA or by operator assessment?
Yeah, QCA.
Because, any little bump on QCA ends up being 20, 30%.
Yeah. And that was interesting because Orbit 2 did not have QCA, on initial. It was site determined. Our initial evaluation of primary procedure. And we had QCA on everything.
Well, that's a more rigorous way, and that'll definitely overcall the 30%ers, the QCA will. Yeah.
So that was it. And the learning curve was virtually non-existent. The other observation we made at the request of FDA was this IVL-induced ventricular capture. Even when you do it in the periphery, but certainly in the heart, you'll see what looks like pacemaker spikes. Well, 41% of the patients had IVL-induced ventricular capture. It's more common if you have a slow heartbeat to begin with. So, multivariate analyses have identified resting sinus bradycardia, meaning less than 60 or less than 65. If you're doing 10 pulses at 1 pulse per second, it usurps the pacemaker function of the heart. It gets ventricular capture. I say a quote electromechanical transduction.
Right.
And, but it is not got enough energy to cause an arrhythmia. That's not been seen. And it was of absolutely no clinical consequence. It's a curiosity. If you get it, your frequency of dropping blood pressure is more frequent, but the magnitude of blood pressure drop wasn't different between patients that had IVL-induced ventricular capture and those that did not. Frankly. So it's no big deal from an interventionist standpoint. If I'm in the lab, it doesn't really bother me. If somebody's really marginal to begin with, Mike, I might tank them up with some volume, barely give them a little neo, tighten them up, and do it. But and you got 10 seconds, that's it. Then you go with the balloon up to 6 atmospheres to see if you get full balloon inflation. And imagine that in that population of patients I just described, the maximum IVL balloon inflation pressure average 6 atmospheres.
Wow.
So it works. It fractures, and we showed that in the OCT. Rich Schlafmitz, had that abstract of the sub-study. You get multiplanar fracture of calcium, circumferential and longitudinal. Nothing else does that, and particularly for the deep calcium, nothing does that.
So that's an important point, Dean. It's going both in circles, the fracture, and along the artery. So you're really disrupting the architecture in 2 ways to kind of open it up. Is that correct?
Absolutely. In fact, following stent deployment, depth of the fractures did change. Width of the fractures, multiple. So it appears that transmural compliance is enhanced by fracture expansion when you put a stent in. That's what it appears.
Now, orbital and rotational atherectomy has been complicated by periprocedural MI, which I'm obviously, as a guy who studied myocardial perfusion for 30 years, not a fan of, and also a high rate of thermal injury and a substantial rate of restenosis. In fact, restenosis rates are about the same as the control arm. So what do we see here in terms of restenosis, and is there an advantage over the thermal injury with rotablation?
Yeah. Well, your first point is absolutely entirely true. After IVL, perforation, abrupt closure, and no reflow, zero.
Wow.
Now, after stent deployment, there was one person had a microperf, didn't get a pericardial effusion, no MACE to 30 days. I mean, this is, a prolonged balloon inflation. That was it in the stent.
Mm-hmm.
That was it after stenting. Prior to that, and this is a bad group of patients to begin with that level of calcium. But to have zero perf, zero abrupt closure, and zero no reflow is striking. Then stent expansion at the point of maximum calcium. That's the biggest arc. And if there were two areas in the artery that had the same arc, it was also the greatest thickness. So that was a two component to what is the area of maximum calcium in this vessel. And the bottom line, 102% stent expansion. Now, in the MSA, minimum stent area, is 6.5 millimeters squared. Do you know what that means long term? I call calcium the gift that keeps giving, meaning if you look at the natural history following stenting, there's a Barantas paper, and there's a recent Guidene and Madhaven and the group at CRF, which looked at 18 trials, 20,000 patients, and did 5-year follow-up. The Kaplan-Meier curves go like this for death, MI, and revascularization. They continue to go apart, even if you landmark at 1 year. So calcium causes late restenosis and thrombosis. Well, at a stent expansion of 102% average, in the worst calcified segment, you're going to have a heck of a lot less restenosis and thrombosis. You should. One could predict that based on that dimension, an MSA or stent expansion. Wouldn't you agree?
Yeah, I think you can accommodate any intimal hyperplasia better through, I was just wondering a little bit more about, with directional and rotational atherectomy, we may provoke more intimal hyperplasia from the thermal injury.
Yeah.
You're not causing that. So, the loss index, the amount of intimal hyperplasia, is it less with
Right.
device? Do we know that?
There, as far as heat energy, I don't know. I think I'm excited to get the 1-year results, and we're going to have that.
So we'll know from the target vessel failure rates at a year how this.
Yeah. In ischemia-driven TLR, I think they're going to be extremely low based on what we know. But again, that's going to be an exciting next step to the trial.
I know you can't speculate, Dean, but I'm going to ask you to a little bit here. What's the regulatory pathway look like for this device?
Well, I think at this point we've hit a home run with the trial as it was designed, satisfied every criteria better than we had actually hoped, And I would hope, since it's been identified as a breakthrough technology, that there would be some efficiency of process. Let me put it that way. And we shall see. I would like to see it, and I can tell you the interventional community would like to see it, early in 21.
Yeah.
Early in 21. I think we've already seen off-label use of the BTK, the peripheral balloons, the S4, 40 millimeters in length, 2.5 to 4 millimeter diameter.
Right.
We're seeing that more and more, and that's not, you know, we
Yeah,
live in a world where sometimes we do that. That wouldn't be my first choice, but
right.
a 12 millimeter long, coronary balloon. And I think it's it's an unmet need. It's a breakthrough technology, and I think the time has come. It's out in Europe, and they're using it. Without any untoward events, in fact, to facilitate cases,
Hmm.
using it in the periphery, as you know. I mean, for us, the first few times I used the device was for TAVR access. And it's been tremendous for iliac and femoral to facilitate access for mechanical cardiac support, for TAVR, EVAR, TVAR. Our guys are using it in the endograph space. And it really has been transformational as far as access, I think.
That's great. Well, Dean, congratulations. I really do think this is a breakthrough technology. Thanks for sharing your results with us. And thanks to all of you out there for joining us here virtually for TCT 2020.